Okay, go ahead.
Okay, great. Students, thanks for being here. This is the ECEE pathway area um, for undergraduate pathways in our undergraduate degrees. We have two speakers today. The first is Professor Lalitha Sankar, who leads the data science pathway area. And then after that, you'll hear from Professor Christian Arens, who leads the pathway and quantum area. So we'll go ahead and get started. And if you have questions for the faculty members, please feel free to use the chat or feel free to take yourself off mute and off and open your camera and say hello and ask your questions that way, whatever you prefer. Thanks very much for being here, Professor Sankar.
Absolutely. Hi, everybody. Thanks for attending this. It's somewhat early in the morning, maybe for the students. So I am a professor in the School of Electrical, Computer, and Energy Engineering. My background is in broadly what's called the signals and systems area. I teach probability. I've been developing this whole program on data science at the PhD and master's level, and I'm sure all of you recognize that knowing this stuff will help you be more marketable even at the undergraduate level. If you see this first slide of mine, of course, there's my name and all that stuff. These four big things there, ICLR, ICML, NeurIPS, and AI Stats, these are the really big conferences in machine learning. This is where the transformer papers, the attention papers, the LLM papers were all published. And if you're ever dreaming of maybe going down a research pathway, this should be some of your goals, right? And the point is to say that there's so much activity happening here. Right. So what I'm going to do in this brief presentation is give you a broad sense of both from a technology and sort of engineering perspective, what the problems are, and then from a broader practical applied perspective, what the courses are and how you should go about doing this, right? Okay, so data science by definition, and I didn't call this AI or ML because they're just the ways to handle data. Data science is actually honestly as old as humans. The people who watched the stars and navigated themselves were also using data. They were using their own internal, simpler scientific methods, which was not perhaps written down like we do now, but passed along by oral traditions. So data science is as old as humanity, but now it's much more concretized because we have computing powers that are far better than us to do things, right? So the whole idea is we constantly make observations. There may be departments upon departments closed by the government, but the government, for example, is a major collector of data because it allows us to make decisions, all kinds of decisions, right? The point is, how do we make those decisions? Computers can do things much faster than we can. So can we use this data and learn in a principled manner? And the whole point is about teasing out patterns in the data. Here's simple examples. Can we figure out if you have an autonomous vehicle, can it figure out if there's an airplane in the pathway? Now that could apparently happen when they fly really low, or another car or a bird. That can also happen, right? How do you do this? This is not as simple as methodologies that were used in classical computer science, and almost all of you here has probably taken a computing class, like, write a program to figure out if this Twitter feed, now it's called X, a string of words has a cat in it or a dog mentioned in it, and so on. Do the texts of videos or Reddit submissions of cats and dogs in it, and the way you would do that is just write a program, right? But when we want to go back to that data collection we had, and we want to distinguish between X-rays that show cancer and no cancer, or X-rays that show a chip, some kind of imaging process that shows a chip having a problem versus no problem, then you have to tease out patterns from the data. And the way that's done, and now this is just a Python program written here, but the way that's done is really, these are very high dimensional data. Like an image, if you parse it and write it out as a vector, the images that your smartphones take are 1 million length long, million pixels, million length long vectors. How do you tease out structures in these? The key idea in machine learning is that there are really low dimensional structures, and we can learn that using complex functions. About 20 years back, nobody would have thought these neural networks would happen. We were still working with simple linear models. We were working with other things called kernels. These are things you will learn in the course. Today, we have these complex networks that sort of mimic the brain, not really, but attempt to mimic the brain, but they can capture complex functions mathematically. This in turn allows us to figure out these patterns, like in this figure on the left-hand side bottom. Maybe there are a few key features that distinguish airplanes from birds and other things. And if you can identify those features, and they should typically be separable because if the human eye can identify those patterns, a computer can be trained to do so too. Training is a word that will come up always in machine learning. We're training an algorithm to tease these patterns. We get to design the algorithm, the way we train, the reward function for training, and so on and so forth. And those are the kinds of things you should learn in a class, in an entire pathways program in machine learning. Okay, so instead of doing classical decisions like you hard code an expert, if you're looking for a string of cat, here you're going to learn what is the decision rule by using data. Okay, so this is another visual way of looking at it. In this pathways, your goal is that you will learn a little bit about data preparation, you will learn about feature extraction, you will learn about training models, you will learn about testing the model you've trained, how you have to keep the training and testing data separate. You will learn about a variety of prediction tasks. And the heart of all of this, mathematically, what you're doing is you're actually working on an optimization problem. And I'll come back to this word optimization towards the end. Okay? And so everything is driven by a measure of goodness. And you keep enhancing that measure of goodness, and you do this iteratively because the data is too large and the problems are so complex. We don't have closed form, simple solutions that you can just encode and solve for. Keeps going back to Zoom. All right, some of the flavors of machine learning that you may have seen are the following. These are like very simple tasks. This is actually as old as 200 years back when insurance became very popular, when the Titanic went out. How did people predict how much to insure the Titanic, for example? Lots of features, shape of the boat, the kind of wood used, the kind of engineers, the company, the people, you know, on the team that will be on that ship. I don't know what it's called, navigating it, and so on and so forth. And today in modern world, we stock market predictions, credit score predictions, temperature, the National Weather Service predictions, Netflix ratings, all of these are regression problems. And we do it with lots and lots of data, which means any individual's data has a lot of features. Temperature is predicted using a lot of sensors that are sent up into various layers of the atmosphere. And it may seem like traditionally, historically, we could do this mathematically by ourselves. Today, we need machines to look at that level of features, okay? Yet another task, which you may all be aware of, is classification, cancer, no cancer, in the healthcare, biomedical engineering, EE, chips default, maybe it's a lemon, not a lemon, maybe in the chip setting, is the email a spam or not a spam? There are so many things within EE and broadly where we do classification all the time. There's yet another setting where we may not have labels. In all these settings, you get data with some clean data, with some target labels, and you use that to train the model, and in comes a new data point you haven't seen in your training data, but you've learned a good function to predict, and so in comes a new data point and you can predict. Same here, you get these circles, you train on that, in comes a new point, and then you can predict. Unsupervised learning is actually really interesting. It's also quite a well-established setting. This is the motivation for modern generative models, or what we call synthetic models, or these LLMs, right? At the heart of it is saying that there are patterns. You can distinguish cows from camels, cats from dogs, birds from airplanes by figuring out those low-dimensional representations, which will cluster further from one another, and similar things will cluster closer. Okay, we've been able to actually figure out taxonomy of human and animal and plant evolution using some of these unsupervised learning. Detecting spread of diseases in a community. This is also unsupervised learning because we don't actually have data with labels sometimes at the outset. All of this requires statistics and algorithms. The probability class all of you take in EE 350 is a great base, and which is why this is a mandatory class for EE students, for learning anything about data science. You need a little bit more statistics, and that's what will be taught in this pathway. All of you will learn how to program in Python. The reality is ChatGPT can program anything you can program and better. But if you want jobs, knowing how to debug ChatGPT's code or build on it is going to become a very important skill. Okay. One of the latest flavors of machine learning, which I'm sure all of you are capable of, curious about, are the generative AI models, where you train on a data and you want to release data that actually looks like the original trained data. This is an image from the internet. Normally it's from O'Reilly's webpage, I think. Now, it to me, as somebody who's been working in this area for over 10 years, it still blows my mind how amazing how we do this. As a theoretician, I'm interested in understanding if we're really sampling from the underlying distribution, if we're learning that well, if there's reasonable diversity and clarity and value in the generative data. Is it just memorizing, and so on and so forth? These are still fundamental questions, but generative AI is not going to go away, and understanding how it works can help you in the longer term, because it's just going to become integrated with anything you do in the real world. All right, so these are the various flavors of machine learning that you should be learning about. In reality, what machine learning does is it uses the observed data to make personal predictions. So literally, you all use music apps like Spotify, you watch shows, you shop, you hope to get credit cards if you've not already. You hope never to go in front of a judge, but maybe somebody wrongs you and you need to make decisions, or you have a family member who did not make a mistake and is struggling with parole decisions, or someday you aspire to cure cancer or AIDS or whatever it is, or drive autonomous vehicles because you want to work while the car is driving, or you want to improve farming. All of this is going to be data driven. And so understanding data science and machine learning is the only way to live in this emerging world as we know it. Okay, so now talking about more of how we do this in EE, we have an incredibly strong faculty in this area. Almost everybody in the signals area does data science. I've listed all the names that we can think of. The blue ones are people who are really strong theoreticians. The rest are awesome researchers in their own area. What makes them even cooler is they are actually applying machine learning to their area. Doesn't mean they're not theoreticians or this or that. Everybody does a mix of theory and practice, but we have faculty who are applying data science to wireless, to speech and hearing, to arts, to AR, to VR, to video generative models, to economics, to signal processing, to wireless, and so on and so forth. That can keep going on. But some of you may be interested in one or the other. Maybe you're interested in doing a Fury or a Moore or a Suri. Figure out your interests as you take more courses in this pathway and approach the right professors. Okay. Of course, the more important question is, what are your career opportunities? If you look at the first line that I've written there, and I've said, if you're really good at training machine learning models and the whole pipeline, sure, you can get jobs at these big companies that I've listed. Honestly, it's going to be very hard to get jobs at those big companies. But those big companies are big for a reason. They feed off a lot of small companies. And so there's really a growing ecosystem of startups in this area. One of my PhD students, who was actually an undergraduate like you at ASU, he went to work for Circle K's R&D, and now he's at a fintech and loving it. And in both places, all the data science, all the optimization, all the machine learning he did as a PhD student has really helped him. So he's really what's called an ML senior scientist. So every area, like even Best Buy needs data science. Everybody needs data science. So you can be marketable more broadly if you figure out how to do that. Now, some of you as EE majors are absolutely in love with chip design, hardware design. I've named again the big companies, but again, it's an ecosystem, right? They outsource smaller parts from smaller companies. Everybody's using data to figure out how to enhance their processes, how to reduce the number of errors they have, how to limit the number of lemons they generate, and so on and so forth. So there are lots of places where data science is going to become important. I also know a lot of our power EE students are interested in power systems. The grid is an incredible example of a network where you use a ton of measurement data. The grid functions today because in real time, we take a lot of sensor data to make decisions. Is there an outage right now? Did we drop load? Did we drop a generator? Is a line out? What should we be doing next? It has been done in traditional manners, but as we integrate more renewables, and that's not going to go away, as we integrate more renewables, the need for telemetry and real-time situational awareness is so important that machine learning algorithms are the only way to do it fast enough. So I've listed some of the big companies again, but APS, SRP, locally, the big utilities like Dominion, the operators, PGM, CAISO, MISO, and lots of others, the labs are always looking for people with strength in power systems and data science. Really, the revolution right now is happening not at Meta, Facebook, Google, Amazon, but really at the companies that need to integrate AI and ML into their pipeline. These can be simple companies, it can be broad companies across the spectrum. These could even be law offices. And your knowledge, or if you have interdisciplinary knowledge, it can really help. Now, I know there are people here who are also interested in physical electronics and photonics, and that, like Professor Jennifer Blaine does, and people like that, and those are applied directly to healthcare, for conservation efforts, to monitor turtles in the sea, and so on. All of that, you put a little chip in there, you're monitoring data. How best to glean patterns? Should you use complex neural network models? Is your data too small? Should we be using simpler nonlinear models? Those are kinds of things you can learn in this pathway that can effectively help you over the long term. Okay. And some of you may still be interested in communication systems and the emerging media revolution, AR and VR. Our president has really been at the forefront of saying AR and VR should be used for education. We at ASU are doing that. Some of you may be aware of that. And all of that is programming, coding, and AI and ML at its heart, right? Most of you also game. How does this work? What can you contribute to that industry if you're that interested? Those are all possible places to actually get jobs. Okay. Very briefly, what are the kinds of courses you need for this? Probability and stats, 350 is a start. Stats will be taught as you go along in your machine learning courses. All of you have a good background in linear algebra, in calculus, up to calculus 3. I strongly encourage all of you to take the Python programming class. We're going to be building up on that. I know many of you do, but that's certainly a part of this pathway. So 203 is something every EE student takes. 350 is something every EE student takes. I would encourage some of you to actually take the signals pathway in parallel with this. Having 3 or 4 would be fantastic, because ultimately, even a high dimensional vector is a signal of sorts. The 2 or 3 main courses that will be introduced in this pathway, the core course is the EEE 394 course that I will be introducing in spring 2026. This is the statistical machine learning for engineers. Okay. 203 and 350 are prerequisites for us, and most of you will come with that. The core course for this pathway, as I mentioned, is this machine learning class. But there are, I'm going to start on a little, so in fall 2025, we're going to introduce the optimization class. It's actually better to take that class and be really well prepared to have the basis to take the 394. Seems a little bit non-intuitive, but that's sort of how it's going to be done. So there's a 498, 591, which will be introduced in fall 2025, which is Introduction to Optimization. It's a much more, it's going to be a much more applied class. It'll actually introduce you to some of the basic algorithms in machine learning, which will make it easier to do the 394 class and do neural networks and things like that in that class. We have a whole bunch of electives across EE and as well as AME. Arts, Media, and Engineering is a interdisciplinary program between the School of Engineering, EE in particular, and the School of Music and Design. And we have some amazing faculty who teach some really cool classes. But the key electives for you should really be Python optimization along with a core. I would encourage you to take one of these other extended electives. Okay, but some of you may be interested in the 4+1, may be interested in grad school, a full master's, or even a PhD. And these are our PhD classes. We have 3 solid classes in the graduate at the graduate level, which is the advanced version of the 394, which is the status 549, an even more advanced version of 549, which is 560, and then a very hands-on deep learning class, which is 513. Some incredible faculty teach all of these classes. You will love it. If you've done 350, 554 is the next thing to do. If you're really a theorist, there are a whole bunch of other classes you can do. If you're more an applied person, there are all these machine vision and pattern recognition courses that you can do. If you're in power systems and you want to do data science for power systems or digital design and so on, there are all those applied classes as well. Okay. I would encourage, and I think this is the messaging many of you are getting. You really like engineering, you're good at your coursework. Yes, EE is challenging, but you love it. Consider doing a 4+1 at a minimum, or a 4+2, because it gives you the expertise beyond the breadth of a bachelor's degree to sort of find the right jobs, to also identify what you are fanciful about, maybe. I mean, what you like in EE, or what you like in computer engineering, what you like in data science. And honestly, I think you know this, and this market has changed in the last 10 years, where there is a demand for people with expertise. So the 4+1 and the masters really help in those ways. By the way, we also have a master's in data science with an EE concentration. So that's also a possibility. We've already built that. There's a PhD program in data science. If you've ever done that, many of these, if you're a bachelor's student and you're really good, you started the 4+1 and now you think PhD is for you, generally you can get it done in 4 years. And there are opportunities to get, that should not be an exclamation, that should be a 1, a first-year Fulton Fellowship for PhD students. Yeah, okay. That is sort of where I am. So looks like I'm done, but yeah, that's sort of it. If you have any questions, I'm happy to take questions until Christian comes on.
Thank you so much for presenting that. Students, go ahead and put your questions in the chat. We've got some time before we hear the next presentation.
There's no shame in asking any kind of question. You should just, anything is game here. You should ask, hey, why should I care about this? Anything is okay. You should ask questions. I mean, if you want.
So I'll ask a question.
Sure.
We hear a lot of students that don't enjoy 350. Do they just gotta suck it up, buttercup, and get through it to get to the fun stuff? So what happens after 350? Why do you just gotta get your way through it?
Okay, this is such a good question. People think, oh, this AI, this is all a software, this is a program. It's not just a program. There's a method to the madness in the way we design these algorithms. At the heart of it is the idea that nature is random. We're making observations from nature, and we need to model these as probabilistic concepts using. So we need that probability to understand everything else that comes later. Certainly probability is not an easy concept, right? I mean, I don't know if people know this, when I teach it, I tell students about the Monty Hall problem and how even some of the greatest statisticians get it wrong about, you open one door, there's two things in the other two doors. A lot of people get these things wrong because it's not terribly intuitive at times. But getting good at it, going to tutoring hours, going to office hours is the only way to internalize the world, which is growing and increasingly becoming statistical in nature. All the decisions we make built on the data we have. We're making this, oh, there's a good chance I will get this job more than the other job. So I'm going to target this. That chance is a model in your head. That's the model we're teaching these machines. Understanding probability is key to designing these algorithms. You may not be in the design space. You may one day become a business person. You may become a salesperson. You may become a marketing person. But knowing statistics, which is a offshoot of probability, is the only way to get there in an effective manner. Lynn, that was a great question. Thank you.
We hear a lot of students that say, you know what, I did 350, I don't want to continue on this path. And I'm like, no. It's important. You have to.
Right, but then maybe it's not for them then, but maybe what we need is, we can talk about this offline, but ways to help them traverse 350 without struggling. It's hard.
Yes. So we've got some questions in the chat. Is 390
Yes.
going to be
What is
available?
390? Yeah, yes, it's going to be introduced for the first time in spring 2026. Yes.
Awesome. And will it be online or just in person for your first run?
Would you recommend I drop? Yes, that'll be my first run. It
Okay.
won't be online.
Okay,
I
in
don't think
person in
so.
spring 26.
Yes.
Okay,
Okay.
I'm about
What did
2
you
weeks
say?
into CSE 100. And after watching this, I'm interested in the data science pathway. Would you recommend I drop and enroll in CSE 110 for Python instead? So that you might want to talk to your
No.
academic
Actually, you know
about.
what? You should do both. Java is a great way to learn object-oriented programming. It's actually very important. If you like programming, you should always learn Java first. Python, you can pick up if you know Java really well. So I wouldn't encourage that. Did you say the 4+1 can also be for PhD? I don't understand this question fully.
So we've got ways, okay? We got all sorts of pathways for you. If you want to do a degree with us, you've got options. We can do 4+1. You can do it as thesis or non-thesis. You can go straight from your bachelor's into PhD, earn your master's along the way. It just depends on what you're interested in, who you're going to be working with, everything like that. So we have the grad school pathway in a couple of weeks, I believe. We'll talk more about it. And you can always reach out to me directly about grad school stuff. So Kobe, I'll put my email in the chat there for you.
Great. Gia, thank you so much for that clarification. That was super helpful. When we're talking 100-level courses, I think it's really good to take them. Nobody in a Python class teaches you a lot about their formatting and coding. Even I don't think that's happening as much it may be, I don't know. But having a very solid base of programming through these classes will really help you when you come to the machine learning programs. So don't drop those classes. That would be my advice.
Great question from Michael.
By the
Given
time we
the rapid
complete,
advancement of AI, do you think by the time that we complete the program in 2 to 3 years, a lot of the skills in machine learning or data science could be redundant or not as sought after or in less demand in the job market?
this is a great question. It is very hard to completely predict this, but this is why, and some people don't like I do this, I teach the course from a very fundamental standpoint. I reinforce the statistics, I reinforce the linear algebra, I reinforce the optimization ideas, because that can help you adjust yourself to any new model that comes along. Okay. In the history of humanity, which is very short, we haven't seen this kind of leaps that have happened. So just to give you a context, in terms of the number of research papers that are being produced in AI, it's about 10,000 a month. None of us can keep up with this. You need AI to keep up with these AI papers and summarize for you. Seriously, this is the truth. We need AI to check the proofs and all that stuff. It's just madness. But it'll slow down. People will not accept some of this unless they have verifiable proof that it's not going to mess up, it's not going to make bad decisions, it's going to be interpretable. Imagine making healthcare decisions and legal decisions, but not knowing what this black box algorithm does. It's already being used, but people can sue for this. So there are lots of broader questions. Knowing the basics will never hurt you. You can easily, quickly read. I mean, I work on generative AI and I can't keep up. And I've been reading, I just listen to videos sometimes to figure out what's this new thing that's come about. That catch up is much easier than catching up on the basics. So having a good foundation is what a university degree is about. It's not the next fashionable thing. So that's how I would explain it.
Awesome. Well, thank you so much. I think we are at time and we need to transition over to quantum engineering. So if students have any questions about this, they should most definitely register for your class in spring and can also reach out to you directly or reach out to me.
Actually, Lynn, they should register first for the fall class. The fall is the optimization class. It'll be helpful for everything, including Christian's class coming courses. It's a very beginner optimization that none of our undergrads have ever had until now. So it's
also just a good idea in general to register for fall before you register for spring 26, because that's how time works.
Yeah. So thank you, Lynn. And I would encourage you, if they go through this pathways, to register for that class. I will be teaching both the spring and the fall and spring classes. So I'm here. If they want to email me, I'm happy to share more details.
Awesome. Thank you so much. All right, let's learn about quantum engineering.
Hello.
Yeah, take it away, Christian. Bye. Thank
Sure,
you.
thank you. Let me share my screen. I hope you can see my presentation. Let me move that a bit. All right, I'm pretty much ready to go.
We're good to go.
Excellent. Perfect. Well, thank you so much. First of all, thank you all for coming. I also want to thank Lalitha for this wonderful presentation. I shall say quantum engineering in general is not as mature as data science and machine learning, but I try to convince you in the next 20 minutes why it is interesting and what the opportunities in these fields are. So in general, what is actually quantum engineering and quantum information science? In one sentence, it is basically use quantum effects to have some advantage, say in computing, in sensing, or in networking. What do I mean by quantum effects? So for example, you see here in the background basically a schematic representation of an atom. Well, the atom contains the world in the middle, because I took that picture because I believe that quantum information science will change the world. But what is so special in this system, this atom? What is special is that it behaves very, very differently than we are used in our daily life. So at the small scale where quantum effects play a role, things are completely different. For example, you could have things happen simultaneously at the same time, even though they're distinct. More precisely, you could have a system that is in two states, say for computing 0 and 1, at the same time. And these effects, that makes actually no sense if you think about it. These are exactly the reasons why we can expect a speed up in computing for certain problems. Moreover, these quantum effects can be used for quantum sensing and quantum networks, particularly building the quantum internet. And the Panther Quantum Pathway program is basically designed to teach you in these new arising technologies that rest on quantum mechanical phenomena. All right, the news have realized that too. So what I'm citing here is an article from the New York Times from 2019. And if you read this, it says basically a quantum machine could one day drive big advances in areas like artificial intelligence, what we heard already before, and make even the most powerful supercomputers look like toys. And let me highlight the next sentence. The Google device did in 3 minutes, 20 seconds, a mathematical calculation that supercomputers could not complete in under 10,000 years. That was in 2019. It was the first time that a quantum device, I wouldn't actually call it a quantum computer, but a device that rests on the fundamental principles of quantum mechanics, outperformed the best known classical computer in a completely meaningless task. But you can see the difference, right? Researchers estimated that the best known supercomputers would take 10,000 years to solve the problem. I would conclude, well, it's not solvable in finite time. But Google could do that with their quantum machine in 3 minutes and 20 seconds. I mean, we're talking 2019, so that was a big thing. So the New York Times obviously wrote this article about it. I shall say a couple of days later, IBM disputed that, and the war is still ongoing, how fast the best known classical machine can do it versus the quantum machine. Nevertheless, that was a big breakthrough where the first time the machine has demonstrated that quantum can be better than classical. And as you can see, these numbers, even though they don't hold up anymore, significantly. There's another article by the Washington Post that basically argued, well, if you use quantum technologies, we have to put the focus on cybersecurity because in the end, quantum computing can crack our best known codes. For example, that encrypt credit cards or emails based on RSA. There is another article by Forbes emphasizing that there's a lot of funding, it was all 2018, in quantum computing because Congress has realized, the United States Congress has realized the need for this rising technology. And in fact, then in when was that? I think it was in 2019 too, that Congress signed the so-called Quantum Initiative Act. It is the biggest funding package in the history of the United States to support quantum research, including quantum technologies. And let me highlight a little bit what actually is. First of all, magnetic resonance or GPS, those are actually technologies that exist that rest on quantum effects. But what this act talks about basically is new technologies that based on these quantum effects. And they have powerful approaches in computing, networking, and sensing. So if you want to read more about that act, please go to the government's website, which I'm saying here. Likely getting renewed this year, we'll see. All right, so what is this quantum technology actually is about, right? I talked here about computing, networking, and sensing. And here I have a picture, actually, what I mean by that. So what you see here, literally, is Google's quantum device. And you see here basically a chip that is mounted into this little weird thing here. These are control wires that go in that control this chip. This chip is in a refrigerator cooled to basically 0.1 Kelvin, even lower, I think, just to came out the quantum effects. Because the main challenge is that quantum effects are really fragile. You have to cool your system down to really, really cold temperatures to leverage these effects. So typically that's when you draw a quantum computer, that's how it looks like. And I took literally that picture from Google. The second thing is quantum networks or quantum communication, very much a classical engineering discipline that you have a communication network here composed of nodes. Around the world. The internet is basically something like that. But now imagine you replace these nodes through quantum computers itself that can talk to each other. In this way, you can think of a quantum internet that rests on quantum effects and that is highly secure against attacks from an adversary. So for example, if you want to send a message, where we say that is Phoenix, from Phoenix to somewhere in Europe, so say Berlin, well, if you want to infer that message in between, say here in, what is that, maybe Chicago, maybe it's Chicago, you would immediately know in Berlin that somebody tried to eavesdrop that message because of the unique nature of quantum encryption. Another effect, which I find quite interesting, is quantum sensing. So what you see here is the schematic representation of a tip with a little spin, which is a quantum object, which you put close to the surface. Since that little magnet, that little spin, which is uniquely quantum, is very sensitive to anything that is on the surface, you basically can sense this surface properties way more detailed than without these quantum features. So those are the three main rising technologies, namely quantum computing, quantum networks or quantum communication, and quantum sensing, that all use quantum effects to do something better. What that actually means is that the field is really multidisciplinary. It combines tools from physics, like quantum physics, obviously, that's the foundation, the language you need to learn, but math, computer science, and engineering. So for you, there's really an opportunity here because I myself am a trained physicist / applied mathematician. But the field has branched out into all of these areas. For example, you need computer science to make it more precise what you actually mean that a quantum computer is faster than a classical computer. Quantum computing, in fact, can be considered as a whole new computing paradigm. You need engineering principles for having communications. And in the end, data science fits in here really well too, because in the end, you need to read out these things and need to process the data. The same holds for these sensing applications. So the bottom line message here is really that we have a multidisciplinary field that came out of physics, or math maybe, but now has branched out in all different areas. So you need to combine the expertise to make meaningful impact here. And the main goal of the Pathway Program is basically to set you up to be experts in this field or to go into industry and actually work in this field. And that in the first glance quite challenging because again, you need all these different tools, but at the same time, it's a huge opportunity because you as engineers can bring in a unique expertise here. All right, so how is the pathway program structured? So first of all, what I teach usually in the fall, it's the pathway class, the 394 class, which is called Quantum Mechanics for Quantum Information Science. So the goal of this class is really to establish the foundation, the language you need to understand quantum technologies. And that language is quantum mechanics. For those of you who are interested, it is typically a 3-level class. I basically don't have any prerequisites because I really want to give you all the opportunity to learn. However, a background in linear algebra, a strong background in linear algebra definitely helps. So if you don't know what a vector space is, it might be challenging to take that class. That being said, though, you can definitely learn that on the fly. So I've seen people excelling in this class with very little background in math. However, think about it as digital design, like 120, right? So you first learn about binary and logic and Boolean algebra and all that kind of stuff, to then finally apply these things to build circuits. And in a similar fashion, you can think of 394. The 394 class really sets the stage. All right, then you can branch out into 4-level classes and learn some specific details, depending on what you're interested in. So for example, right now I'm teaching 498 and 591, also listed as undergraduate and graduate. I basically teach quantum computing, the foundations of quantum computing, what it is good for, how do you build a quantum computer, what will be the impact of this new technology be. It helps very much if you have a background in quantum mechanics here. So this elective definitely rests on the pathway class. So if you have not seen quantum mechanics before, it is really, really challenging to take the 498 class. So I would highly recommend take the fall class, the quantum mechanics class, and then branch out in the spring, either into something more theoretical about quantum computing, or Professor Gorel is basically redesigning this class right now, the 434, which is quantum mechanics for engineers. Traditionally in this class, you learn basically quantum mechanics and apply it to semiconductors. Professor Gorel told me that he aims to redesign this class to focus more on how to build quantum devices that are used in this new technology. We aim to add to the pathway program more tentative courses like quantum control, where you apply control engineering principles to quantum physics or quantum mechanical systems. Quantum optics, which is nothing else as studying and leveraging the interplay or the interaction with light, which we describe basically quantum mechanically, and matter, which are atoms. That is quantum optics. Open quantum systems is a key discipline where we learn about noise, because the main challenge in building a functioning quantum computer or making quantum technologies work is noise. The main problem we face right now is actually that these quantum features we want to leverage are extremely fragile. They're extremely sensitive to disturbances. In order to address that, we need to talk about noise and how we mitigate that. And the setting in which we learn about this is typically called open quantum systems. The next one is, of course, we want to build these things. So we also want to offer at some point a course that is called quantum device modeling. All right, so the pathway program is fairly new. We hope to continue adding classes to it. So what we have right now is just these 3. But again, hopefully in the fall this year, we have more to offer. All right, so what the heck can you do with this? I mean, I showed you all these news, right? There's a lot of funding and money and everyone's excited about it. But what are actually the job opportunities in this field? Let me just give you a brief overview because it pretty much changes every day. So the first thing I'm going to list here is just a subset of companies and startups that work on quantum technologies. There's many, many more, by the way. So the most famous one, obviously, IBM and Google. They have the actual quantum devices. In fact, you can access IBM's quantum computers through the cloud. ASU has a special contract with IBM that allows you to run actually quantum algorithms on quantum computers, namely IBM's. But Amazon, Q-Control, those are all, or IonQ, those are all big companies now at the stock market, as far as I know, especially IonQ, that pursue quantum computing. But I also put here HSBC and JP Morgan. You may wonder, wait, what is this, right? Because those are banks, financial institutions. Why are they interested in quantum computing? Well, I think the interest is twofold. They first of all have research groups that work on quantum computing. For example, to develop algorithms that make stock market predictions such that they can make their investments better. So there's a big application area in finance too of quantum computing. That's why these banks are very much interested in pursuing this research. But second, I know people who work at JP Morgan as quantum engineers, as advisors, basically, to advise people who should get into this or not, whether there's something to it or not. The question is, should we invest or not? And if you have a background in quantum engineering where you can advise the big bosses, basically, whether to put some money into that or not. All right, so there's many, many more. And what I plotted here up to 2022 is basically the number of quantum startups per year. So that's the y-axis as a function of the year, which is the x-axis. Well, as you can see, it goes up, and then there's a sharp drop. Guess what that drop was? Sorry, give me a second. Well, it was COVID, but now we see the trend again going exponentially up. So that field is growing very, very rapidly. But besides companies and startups, national labs such as Sandia National Laboratories, Los Alamos National Laboratories, or Berkeley Labs, they are also very much interested in quantum information science because of national security implications. Last but not least, and I want to emphasize this, with academia, we need people who teaches this, right? We need people who build the labs, who basically design new teaching tools, pedagogy around this whole new technology. Because again, the challenge is you have all these different disciplines coming together to make quantum engineering. So the field is continuously growing. There's a lot of hype around that right now too. So a big part of the program is also to learn what is real, what can we expect in the future, what is the potential of these technologies, but at the same time, lower a little bit the expectation and say, look, there is something to it, but this is hype, really, that you'll be able to distinguish. All right, with this, I would like to thank you for your attention. If you have any questions, please let me know. My office is actually in the Goldwater Center, the 4th floor, 411B. Feel free to drop by anytime if you have questions. Shoot me an email. I'm happy to talk more about this exciting field. Thank you.
Thank you so much. Students, go ahead and put your questions in the chat. A question I have for you, Dr. Arens. So right now, you are our quantum faculty.
Yes, I guess that's actually, it's interesting that you say that because I saw the presentation by Professor Shankar, by Lalitha, and like she lists all these faculties working in these different areas, and I would love to do something similar, but yeah, it's just me at this point.
I know, we're working on that. We always enjoy having people from industry or national labs, you know, engaging with our students, teaching classes, stuff like that. How do you see people that are out there in quantum information science right now? How are they interacting with students? What are they looking for? How can we build a good relationship with people in the industry, because we don't have a ton of faculty in this area to rely on?
Right, so it's twofold. First of all, there's a huge need for this. So I work closely with people at Sandia National Laboratories, at IBM, and at Berkeley. And they all tell me, well, we don't have the work power to work on these things. We need more people, right? So since the field is fairly small currently at ASU, me as the only faculty doing this, so how do you get to know these people at Sandia or at Livermore or Los Alamos, right? So what I typically do is I invite people from Sandia, Los Alamos, et cetera, to give presentations, and I run the so-called Quantum Seminar Series. So at the seminar series, I invite people from these national laboratories to talk about their research, but also about careers in this field at the national laboratory level or at the university or at any other companies. So I think that is a really, really good opportunity for students, first of all, to attend these seminars, to learn about this stuff, but also to directly talk to the people at the national labs and learn more directly from them what the opportunities there are. So for you guys as students, if you see an announcement about a quantum seminar you're interested in and you want to learn more, I would highly encourage you to come, because it is pretty open, it's pretty informal. So the idea is really to chat with the researchers in that field and see what the opportunities are. Well, but let me add to that. Of course, we hope to grow this field, and we hope to have more faculty in the future that can set you up even better to connect to these people.
So if students are interested in the quantum area, why do you think that they should choose ASU compared to another institution to study this topic?
That's a great question, Lynn. First of all, ASU is great. It's really nice. I mean,
Congratulations, you keep your job. I won't. That was the correct answer.
no, but also, so when I joined ASU as faculty, that was 3 years ago now. I was really, really excited because there is so many resources in the Valley. That is, for example, I have now access to IBM's quantum computers, right? I think ASU is the only university in the United States, well, North Carolina, NC State, that is a so-called IBM Quantum Hub. That means we have privileged access to IBM's quantum devices and can play around with these quantum computers, right? No other university has this. Well, you can buy this access and you can join other universities, but among NC State, ASU is the only one who is an IBM Quantum Hub. So that was for me quite exciting when they told me, hey, you can actually use a quantum computer. I was like, what? That sounded really exciting. Besides that, the engineering program at ASU is amazing, right? As you know. So it combines many, many different aspects, including quantum. So what I try to highlight in this presentation is that coming into this field with a strong engineering background that exists at ASU to learn about that, that is a unique opportunity you get here, right? Because in the end, it combines stuff, right? Data science, control engineering, the things you heard before, they are very much applicable to quantum too. And basically adding to the existing programs at ASU such that together with the other programs, you create something new. That is, I think that makes ASU really, really unique. And I think that will have a long lasting impact because you need these different disciplines to address these challenges.
Yes, and so this pathway was our first new addition in pathways in decades, years, I don't know, in the undergraduate curriculum. So there's a lot of interest about it. Students are really excited. And it just goes to show that, I mean, whatever you want to have happen here, we can have happen here.
Yeah, exactly. That is my message too. So the size of ASU resources in general, that makes it a really unique place for quantum research in particular, but I think any research in general.
We've got a question in the chat. Is the intro class, so the 394, just in the fall, or could it be taken in spring?
That is a really good question. We offered it, I think, last year also in the spring, but unfortunately, we don't have the workforce to teach it in the spring because I teach quantum computing in the spring. So as of right now, we offer just once a year, and that is in the fall. We try to change that in the future, including also the spring class, such that you can really get into the circle whenever you want, but also add an online option. So we also would like to offer it in a hybrid fashion in the future. But again, step by step. So far we have 2 classes. Unfortunately, you should take it in the fall and then go into the quantum computing class.
Yeah, and if you're looking at your schedule and you're not sure how it's all going to fit, reach out to your advisor. We can take a look and see how, things can move around and we can shift things in.
One thing, let me add, because in the quantum computing class I'm teaching right now, even though I said before you definitely need quantum mechanics background or math background, that is true. Let's put it this way, that makes life much easier. I have a handful of people now in the class that never seen quantum mechanics before. That is possible. It's just a little bit more work. So if you feel comfortable with the math behind it, then I encourage you also to take the class directly, the quantum computing class. But from experience, it's significantly easier if you take quantum first.
Definitely. And so students, with that kind of conversation, you definitely want to talk to the faculty to kind of understand what is your baseline knowledge, and talk to your advisor to say, I'm feeling a little low in this. My workload for all these other classes is going to be really big. How is this all going to work out for us? So if you ever have questions, talk to the faculty and your advisor.
Yeah, let me actually show you my cover slide again, because feel free to reach out anytime. I did not put my office here. It's 411B, so 4th floor, Goldwater Center, 11B in the Sensip area. Literally, drop by anytime. I'm most of the time in. If not, shoot me an email and I'm happy to chat more.
Yeah, and Savannah's asking, would it be possible to get a copy of the course info for both of these pathways via email? If the Zoom recording isn't going to be sent already. So we will be posting the Zoom recording on our website. But Savannah, you can reach out to your advisor and we can get that information over to you.
Yeah, also, if you want to know the syllabus of both classes, please send me an email. I'm happy to share that with you.
All right, we'll give it a couple of seconds just in case anyone's typing in a last minute question. But otherwise, thank you so much for joining us today, Dr. Arends. We really appreciate it.
Sure.
And thank you, students, for joining and having such great questions.
Right. Thank you all for organizing, and well, hope to see you someday here in one of the classes.
Yes, absolutely.
Right. Bye-bye.
Bye. Thank you.